So we're going to take a look at 3.4, which is mixed and entire radicals. So what is another way to write 10 over 20? Well, 10 over 20 could be reduced all the way down to 1/2, which we can write in infinite number of ways. So 5 over 10, 15 over 30, all kinds of different things. So what we're looking at today is a different way of writing something that is still mathematically equal. So we can also simplify and write equivalent radicals. So if you look at the difference between these two, we have the square root of 9 times 36, where both are underneath the radical, and we have the square root of 9 times the square root of 36. If you do these in your calculator, we would say we need to multiply first here. So we would do 9 times 36 is 324. The square root of 324 is 18. In the other case, we would have done the square root of 9 is 3 times the square root of 36, which is 6. That still equals 18. So note that it doesn't matter if the numbers are multiplied underneath the same radical or if they are multiplied next to one another under their own radicals. Same thing will apply if we've cube rooted something. We multiply these underneath the cube root first and we get 1,728 when we cube root that in our calculator. Remember, to cube root something, you're going to press math and select number 4, which is the cube root of something, and you'll put your number in there. All right, if we did the cube root of 27, that is 3 times the cube root of 64 is 4. 3 times 4 is still 12. So we proved it in both a cube and a square. So the law for simplifying radicals looks something like this. It looks a little convoluted. So the nth root of a times b is equal to the nth root of a times the nth root of b. So, for example, let's do the square root of 16 times 81. Why not? Remember, this is a 2 here. We just never write the 2. So n in this case was 2, a is 16, b is 81. This will be equal to the square root of 16 times the square root of 81. All right, which would be 4 times 9, which is 36. So list the perfect squares, the perfect cubes, and the perfect fourths, so that you kind of get a feel for what they are. They're important to know. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc. Onwards and upwards. You might have more room on your paper. I'm just going to run out of room here. Okay, the cubes. 1 cubed is 1. 2 to the power of 3, or 2 cubed, is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. So notice they grow quite a bit faster, your numerical value. The fourths, 1 to the power of 4 is 1. 2 to the power of 4 is 16. 3 to the power of 4 is 81. 4 to the power of 4 is 256, and 5 to the power of 4 is 625. Okay, so just be familiar with these. I like to write them out at the top of my paper as I'm working, or keep them handy to look at so that they're just a little bit quicker to find. So write these radicals in simplest form. Simplest form means we are going to write them as a mixed radical. Okay, so what we could say is that 44 is the same as 4 times 11. So I could write this as the square root of 4 times the square root of 11. Now this is really great because the square root of 4 is 2. Now we can't square root 11, so we will still say that it is times the square root of 11. We write this without the multiply, we just say 2 root 11. So what we're going to look for is the perfect powers that might multiply to our number. All right, so let's look at the next one. The cubed root of 54. Cube roots, we're going to look at 1, 8, 27, 64 is already too big. So 54 divided by 8 doesn't quite work. So we'll look at 27. 54 is 27 times 2, so we could write this as the cube root of 27 times the cube root of 2. Again, because 27 times 2 is 54. So the cube root of 27 is 3. The cube root of 2 is not a nice number, so we leave it in its radical form. So 3 times the cube root of 2, or again, we just forget the little multiplier in between and write that. All right, last one, the fourth root of 48. So we're going to look at our fourth powers. We never use 1 because the square root of 1 is 1. Very uninteresting. But if we look, 48 is equal to 16 times 3. So I can write that the fourth root of 48 is equal to 16 times the fourth root of 3. So the fourth root of 16 is 2. The fourth root of 3 is not a nice number, so we're going to leave it as is, and we'll write this as 2 fourth root of 3. Okay, these are all called mixed radicals. Mixed because we have a whole number and we have a radical out front. We can also simplify using prime factorization. It looks like a little bit more work, but sometimes it makes it a little bit clearer. Okay, so I will try 150. If we factor 150, it is 2 times 3 times 5 squared. So I'm going to write that in. So we can say that this is equal to 2 times 3, times 5 times 5. So I'm going to write that out. If something's written twice underneath a square root, it can come out of the root. So it's like saying 2 times 3 times 25. Well, we can square root 25. It is 5, so it comes out of our square root. So we will write this as 5. Now 2 and 3, there's only one of each of those underneath the square root, so we can't take them out. So 2 times 3. We'll write this as 5 root 6. Now, if you wanted to check your work, how could you do that? What you can do is you can find what the square root of 150 is. And we want to make sure that in the end, that number is equal to 5 times the square root of 6. So we'll find what this is in the decimal form, what this is in the decimal form. They should be identical. All right, go ahead, pause this video and factor 128. So 128 is 2 to the power of 7. Therefore, what we're going to write is the fourth root of, and I'm going to write them all out, 2 times 2 times 2 times 2 times 2 times 2 times 2. Now, what we could do is the fourth root, we need 4 of these to multiply together. So if I have 4 of them, we can take them out. All right. So if I have 4 2's multiplied together, when it comes out of the fourth root, it becomes a 2. What's left is 2 times 2 times 2. Now I can't take that out because there's not enough 2's. There has to be just as many as this root itself. Therefore, we will write this as fourth root of 8. Last one here, 108. The factorization of 108 is 2 squared times 3 cubed. So therefore we can write this as the cubed root of 2 times 2 times 3 times 3 times 3. Because there are 3 3's, I can take them out and it will be written as 1 3. And the cubed root of 2 times 2. Can't take the 2's out, there's not enough of them. So we'll write this as 3, the cubed root of 4. So any radical, such as the square root of 6, the cubed root of 244, etc., is called an entire radical. So an entire radical, the entire number is underneath the radical. A mixed radical, such as 4 cube root of 3, the square root of 3, 3 cube root of 10, etc., is called a mixed radical. Mixed because there's a number out front and there's a number underneath. They are in a mixed format. Entire, everything's underneath. A mixed radical, it's split. We also call this the simplest form. Okay, it's like when you reduce a fraction until it can't be reduced anymore. That's what a mixed radical is in the world of radicals. Okay, write these mixed radicals as entire radicals. So what we want to do is we want to take the number out front and put it underneath the radical sign. So in this case, we need to put 7 underneath a square root. So we want it to still be the same thing. So if I want to put 7 under a square root, I need to have it 7 times 7, because the square root of 7 times 7 is 7 itself. And this will still be multiplied by 3, root 3. So we bring those two together, and we get 7 times 7 is 49 times 3. Okay, so I'm going to write them all underneath just to simplify one more time. It's kind of like going backwards here, and we get that this is 147. Okay, again, I can check to see if these are equal. I'll write the decimal out of 7 root 3 and of the square root of 147, and they should be the same number. Okay, looking at our next one, 2 to the cubed root of 4. So for 2 to remain the same under a cubed root, we need to multiply it by itself 3 times. So times the cubed root of 4. Putting them all underneath, we'll have 2 times 2 times 2 times 4, which is the cubed root of 32. Double check your work, see that the first statement and the last statement are still equal. Third one, if I want to put something under a 5th root, how many times am I going to have to multiply it by itself? 5. So under the 5th root, we'll have 2 times 2 times 2 times 2 times 2 times the 5th root of 3. And when we put them all underneath the same 5th root, we end up with 5, the 5th root of 96. Okay, a little bit of a word problem idea here. You have the following cone. Determine the slant in the simplest form. The height of this cone is 3, and the diameter of the cone is 12. Therefore, the radius is 6. Right angle here. So we can use Pythagorean's theorem to find S. We will write 3 squared plus 6 squared equals S squared. And again, that came from A squared plus B squared equals C squared. 3 squared is 9. 6 squared is 36. And that will equal S squared. So S squared is equal to those two added together is 45. Now to get rid of the square, we have to square root. So S equals the square root of 45. Now that looks great, except we need it in its simplest form, which means I need to write it as a mixed radical. So we could say that 45 is equal to 9 times 5. Now, why did I choose 9? Well, it's a perfect square. So under a square root, it'll look really nice. So the square root of 45 we know would be equal to the square root of 9 times 5, which is the square root of 9 times the square root of 5, which would be 3 root 5 as our final answer. So again, simplest form means we're writing it as a mixed. Write the following radical in simplest form. So pause this video, take a look, and try it on your own. What you should come up with is exactly what we just saw. The square root of 45 is 3 root 5, okay, based on our last question. And the following mixed radical as an entire radical, we need to bring the 2 underneath. So that will be 2 times 2 times 2, whoopsie, under a cube root times the cube root of 4, which is the cube root of 2 times 2 times 2 times 4, which is the cubed root of 32.